is going to be a very exciting video on interrupts. This video assumes that you have gone through the previous 3 videos and also that you understand the distinction between two concepts. Okay, first, what is a synchronous event and what is an asynchronous event? Now, we need to understand that both synchronous and asynchronous events need to be handled by the CPU. Now, if you have studied 8051 or 8086 or any other microcontroller, or if this is your first microcontroller, we need to understand that generally a microcontroller needs to respond and reacts to events external to it, outside it. So those might be button presses, clicks on the keyboard, mouse, sensor input data, or you need to react when a temperature is below or a humidity is above, or any special events that you are tracking, or you immediately want to raise an alarm. Okay, so all these are classified as interrupts. Okay, now the word interrupt is well defined. So RISC-V has a concept of a trap. Okay, so now a trap is any circumstance or any situation where the CPU needs to stop what it is doing and then run code which corresponds to that particular event. All right, so generally one example I will give, generally you're going through your daily life. Okay, sometimes you fall sick. There you stop your activity, then focus on healing and come back. But you will pick up your work where you left off. Just imagine this in mind when we are talking about interrupts. Now, what is an interrupt? Like we told you, in microcontroller lingo, an interrupt is a mechanism that allows a peripheral. A peripheral is something outside the CPU but inside a microcontroller, right? That needs to interrupt or stop the normal flow of the CPU. Now the CPU at this point will save what it is doing, immediately serve the interrupt or run a function that is supposed to run when this interrupt happens, and then it has to resume its work, right? Now the interrupts are very important because you need to have a mechanism to react to external events. And next, sometimes your phone or your device enters into low state mode. Right now my screen is not on the phone, but the moment I do something, it returns back and shows the home screen. All right, so basically efficiency is important where you are dealing with battery devices or you have multiple events that you need to handle, right? You need to be able to switch among them. So very important role interrupts play when you're dealing with RTOS, when you're dealing with determinism, okay, when you need to react to events. And what most important example I can give you is gaming, right? When you're playing your PUBG, or I don't know what kids are into nowadays, but the latency is very important. The moment you press shoot or the moment you click on the screen, you want the event to happen or the corresponding action to take place very immediately. So that is why we have the concept of interrupts. All right, now let us understand what an interrupt is. Okay, visually. Now this is your main loop in your program. It is doing its job. Now the interrupt has occurred. Now what to do now? Basically you have to jump or run a function, but you can't immediately jump into the function. At this point of time you store your work so that when you return back from the function, you go back to the previous address or where you left off here. That is called the jump execute ISR and return to ISR. Remember this. You have a normal mode of operation. Something happens. You have to save your work. Jump to that place. Execute that piece of code and return to where you left off. If you understand this concept, then 90% you understand what an interrupt is. That's it. Now, there are two types of these events. One we call an exception, the other is an interrupt. Now, exception is a case where you divide by 0 or the CPU doesn't know where to go next. Now, exceptions are not handled in ISR. Their exceptions have their own function which is called, now that function is called a handler. Same, but different, okay? But both exceptions and interrupts are classified as a trap. Exceptions are synchronous, which means they happen along with the CPU clock or with the current instruction cycle. But interrupts are asynchronous. They can happen anytime. They are not tied to the CPU. The CPU might be doing whatever, the clock might be in whatever, but when an interrupt comes, it's asynchronous. All right. Now, RISC-V calls both these events trap. Once the RISC-V CPU enters a trap mode, then it goes to the CPU goes to an elevated execution mode called the privileged execution mode, where hardware comes into play and it decides what to do next. All right. Now, let us see this at the platform level. All right. Now, what is the PFIC? Okay. The PFIC is a platform level interrupt controller. Okay. Which is called programmable fast interrupt controller. Okay. And it can handle 255, which means anything that fits into a byte. Okay, 255. That many interrupts it can handle. Now, on this particular IC, there are 23 peripheral interrupts. Okay. And each interrupt has its own independent trigger and mask control, which means that it doesn't mean that all 23 peripheral interrupt needs to be handled. They are programmable. You can select what you want, and you can also decide whether the ISR needs to be called at that point of time or not. All right, that's all it means. Next, you have multi-level interrupt nesting. Now, this is an advanced concept. Basically, what if two events occur at the same time? What do I do? And fast interrupt entry and exit mechanism. Now, as I was explaining here, this jumping to another code and exiting back takes its own finite amount of time. Therefore, you have a very fast mechanism to jump and return. Vector table free access. Now, when you have 23 interrupts, these are placed in a table called as a vector table. Okay. Now, vector table free access means that you know where to jump without looking at this table. That's all it means. When the fast interrupt mechanism is enabled, generally normally what happens when an interrupt occurs is the CPU has to decide which entrance should I jump to or which interrupt handler should I call. And it looks up to the table one by one in a for loop. Now, if you are dealing with the last interrupt, you have to go to the 14th index, all right, or whatever, 18th index. But when you have vector table free access, you directly jump the moment the event happens, and all of this is handled directly in the hardware. All right. So this is a very brief way of explaining, but if you want to go into the depth, please go through the reference manual. All right. Now, these are the interrupt sources, but in this session, we are going to concept in the EXTI, external interrupt, which means connecting to buttons or connecting to triggers outside the controller over the GPIO pins. That is what the external interrupt is. I cannot cover every kind of possible interrupt in this session. We are only looking at one example of an interrupt, which is the external interrupt. Okay. Now, I'll just briefly go over the interrupt mechanism before going through the code and the demo. Basically, the programmable interrupt controller, okay, the PFIC, programmable fast interrupt controller, you can program it to set the interrupt priority. You can enable or disable which interrupt you want and the address to where it should jump. All right. So within the CPU also, we have four registers which are controlling this activity. First is the mcause register, which means when the interrupt happens, the CPU notes down, okay, why this happened. Next you have the mtvec, the machine trapped vector register. So basically I told you, this is the mechanism by which directly the jump takes place the moment an interrupt happens. Next is the machine interrupt enable. If the interrupt is not enabled, there's no reason to jump. And the mstatus. The mstatus basically contains the state of the MIE bit. Okay, that's it. Now the moment an interrupt happens, first the FPIC checks for the priority, whether I should serve it. Okay, interrupt priority basically means that some interrupts have more importance over others. Obviously, like if a colleague is calling you or a manager is calling you, obviously you will try to answer the call of the manager first. All right, just an example. Now suppose you have 2 or 3 interrupts that are coming in the same place, same time, then not just the priority, but there is a nested vector control. Like if 2 button presses happens, but both the button presses are of same priority, what to do? You have a vectored nested mechanism. Nested means one inside the other, nested. So all this is handled for you in hardware and software. You don't have to worry about it. You just configure it properly and the RISC-V ecosystem takes care of everything. So when the FPA, when the programmable interrupts happen, right, the priority is first checked. And then lower priority, the lower rank, this is called a rank. Lower rank has high priority. Now the non-maskable interrupt, which is having -2, has the highest priority. All right. This is a reset. NMI is basically the reset button. The moment you hit it, code goes to the execution or of the main, okay, or the entry point where you are supposed to start the program. It goes back. It's a reset function. Next is the hard fault. I will show what the hard fault is. Basically, it's a trap. Hard fault is a trap. All right, and this is handled in a something called error handler, which also we will see in code. We will not execute, but we can see in code. Next, we have a timer interrupt. Similarly, all the other peripheral interrupts, we have 23 peripheral interrupts, as you can see. Now, the moment the programmable interrupt controller decides that I have to serve a particular interrupt, it will save the state, it will jump, it will run the interrupt code, then it will clear the bit which says that this interrupt has been served, and then you restore the CPU state and run to the main program. That's it. Now, an important distinction is that this is limited to this particular microcontroller. Other RISC-V architectures, like if you see the Raspberry Pi Pico 2, Pico 2, RP2350, it has a different way. It doesn't have a fast interrupt control mechanism. It has a platform level interrupt mechanism. All right, that is outside the scope of this video. Now that we know what we are dealing with, we'll take a 5-second break I will set up the hardware and then we will see a live demo and coding. All right. Hi guys, welcome after the break. Now I have connected my hardware with a 5D rocker. A 5D rocker is nothing but a sequence of 7 switches. Okay, I've got this online for like 81 rupees. All right. So what this allows you to do is it's a collection of 7 switches. Okay, like up, down, left, right. So we can also understand how our joysticks work. Okay, it's a rocker because it, unlike a joystick which gives analog value, this gives a digital value 0 or 1, and that 0 or 1 is depending on the common end. Okay, if your common end is VCC, every time the button is pressed, right, it gives you VCC signal, and every time the button is depressed or released, it will give the default which is high. So similarly, whatever is in the common pin, VCC or ground, that signal will appear whenever you press the corresponding button up. Okay, it's a rocker, you don't press up, you just move the rocker forward like we will be seeing here. Up, down, left, right, and it also has some set and reset buttons. Now the set and reset buttons don't mean anything. You have to configure them the way you want. All right. So I have connected the common as VCC, which means by default my system will be in a low state, and whenever I want the system to experience an interrupt, I will press the button and it will go to the high state, VCC, basically rising edge. All right, let us see this rising edge in action. Now I've connected this entire setup to a logic analyzer. All right, basically a logic analyzer that you can see here, this one, this logic analyzer will allow us to see digital signals. It's cheap, you can get it on the same website. So the moment I press the button, you can see that the logic analyzer shows the rising edge. All right, this particular event that happened, we call it as a rising edge, and upon zooming we see that the edge is not perfect. All right, now that behavior, we have one more example here. You see these pulses at the end or beginning. That is because these switches are not perfect. They have a behavior called as bouncing. And to prevent this, whenever we are servicing an external interrupt from a switch, we need to also perform another activity called debouncing. All right. So we are also learning debouncing in this video. Now, let me just explain what this debouncing is. Now, as we have covered in this section, the button is connected commonly to VCC, which means whenever I press it, the state will become 1, and by default the state is 0, and we want to detect a rising edge. All right, what you do with debouncing, there are many ways to debounce. Okay, software, hardware, and etc. But this probably the simplest way to do it in software is the moment you detect a rising edge, that is a transition from 0 to 1, you neglect all other rising edges for a period of time. Now that period of time where the next successive rising edges are neglected is called as a debounce time. That's it. Right? We can better visualize it while we are looking at the code. Now let us go into the code. And the important thing to note is you have a startup file, okay, S file, where all the locations of the interrupt handlers and ISRs are given. All right, and this is the vector table. recall. And it's possible that we write assembly code here, and the moment the interrupt is enabled, that this code will execute. Okay, but I'm not going to do it right now. Instead, we can use plain old C and by overriding this. So basically this weak handler, all right, what this says is leave place for me. When this function is written in C, you replace that code here. That's all it means. It's a weak handler. Okay, and this attribute is a macro, like it tells a compiler to classify this under the interrupt section with a fast interrupt mechanism. All right, so if I hover my mouse on it, I get some help. So basically this enables BTF, vector table free operation, the moment I hit this. Otherwise the interrupt time will be slow. Now interrupt timing is important when you're dealing with pulse width modulation or other advanced concepts with timing. All right, now I have written a function called exti extra interrupt pd2 init. Now if you see the previous video where I'm discussing memory map peripherals, you'll know how to write this. First I need to enable the clock. Next I need to set which pin and set it for pull down. Like I said, I'm looking for a rising edge, which means default behavior on that pin should be low. The input is pulled down forcibly. Next, we need to have a small delay for the pin to stabilize because it won't come down immediately. Next, we need to connect the external interrupt line to PD2. All right, now this concept is important because there are 7 EXT lines corresponding to the 7 ports or the 7 pins of a port. All right, now if you look at the data sheet, you will know how this connection is taking place. But for PD2 you need to connect EXTA line 2. All right, and then we have set up the mode. The mode is how the interrupt behavior is discovered. All right, so I want the EXT to run in the interrupt mode, and then I want a rising trigger. So I want my vector table, I want to jump to the vector table whenever I detect it, and then I enable this. This enables the global interrupt for EXTI. So generally, even if an interrupt is come, the CPU ignores it. But if this bit is enabled, definitely it will take action. That's all it means, right? Next, we need to clear any pending interrupts before entering into the nested vector interrupt controller. Now, again, what this means is NVIC means nested vector interrupt controller. When I'm dealing with 1 or 2 interrupts at the same time, whom should I give the priority to? Now this is standard code. I'm only expecting 1 interrupt at a time, so I put the default values. But in future, when we are dealing with 2 or more interrupt sources, we need to configure the NVIC also appropriately. Okay, just bear in mind. Next, this is the handler. Now I told you the handler is the function that is executed whenever the interrupt happens. Okay, so first I will check whether the interrupt is actually triggered. When the interrupt is triggered, the interrupt status on the EXT line will no longer be reset. It will be something else. Now, once I enter into the interrupt, I will clear the pending flag. All right. Next, I will check whether the state is actually high, because in a rising edge, the pin state will no longer be ground, because see, the pin is pulled down. But when the interrupt happens, the pin is set high. I'm checking for that. Next, this is a simple debounce. Whenever the global variable, that is debounce active, is enabled only, I want to perform the interrupt processing. This is the interrupt processing. I'm just incrementing a variable. That's it. All right. In the main, now this I can do it outside of the main using a timer also. But since we don't we have not arrived at the timer yet. I'm performing in the main loop. Okay, it's just a simple loop that resets the debounce time. That's it. All right. Now this code will be available in a GitHub gist or in the pinned comment, so you can go through it. But for now, let us see the demo. All right. Now let me go back to my logic here and run this and check if yes, I'm able to see. Now this way we will be able to see the code and the interrupts also. All right. Now I will run and I will jump into the debug mode, and already I am checking for two variables, whether the switch is pressed and what is the counter. All right. I don't need disassembly for now, but this is a much better view. We see what is happening. All right. Now let me run this. Now you see nothing is detected. Now let me run the code. It went low. The pin went low. All right. Now I'm clicking. I have clicked approximately 7 to 8 times. Let me pause and check the variable T. Okay. 13 times. Okay. Now let me continue my operation and click 14, 15, 16, 17, 18. Pause. You see the count is 18. Okay. Now we will just summarize what has just happened. Every time the button press happens on PD2, the EXTA unit or external interrupt unit detects a rising edge. And next, the global status is checked, whether the interrupt is enabled or not. If it is enabled, okay, then it's checked if the MEIE, it's another register, whether the external, this is a global interrupt enabled, whether external interrupt is enabled or not. Okay, next, you save the context, that is save all the 16 registers of the CPU. Then you set mcause. Mcause is an assembly instruction that tells you what happened, and then due to the VTF or vector table free operation, immediately the vector address is also stored in by hardware, so the lookup is bypassed. Okay, the table lookup is bypassed, and then immediately the external interrupt handler is executed, and then we perform the ISR, we check the status, we clear the flag, we handle debounce, and then upon exiting, immediately the hardware or the mret is placed. The mret is an instruction that is placed by the compiler, which will restore the context and run it back. So this is a complete picture. All right. Button press, trigger detected, then checking and debouncing. Then we use the VTF mechanism to jump to the interrupt immediately. Then we clear. All right. Thank you.